Next up, we have Professor Phil Dustin of the College of Charleston, giving us insights into the science of the climate crisis. Let's hear it for Phil.
Wow, that was quite a talk. I don't know where I can go from that, but I'm a scientist. I study coral reefs. I teach ecology at the College of Charleston, and this is my first public talk in 2 years. So it's an interesting one. We'll see how far it goes. But what I wanted to talk about is the difference between facts and beliefs, because that's what science is about. You know, we start off, science is really a way of knowing. It's not the scientists and everything. No, it's a way of essentially having questions from curious people, and we have a way of approaching that to try to find out what the real answer is, and that becomes knowledge. And with knowledge, then, we grow our research and we continue that down the road, and it leads to what we think of as critical thinking. And critical thinking is not being critical of somebody, but looking at something from all sides and trying to understand it. So life on Earth, and Earth itself is a planetary phenomenon. You will never find a planet with half a life on it, you know, like one side is like Mercury, one side's hot, one side's cold, one side has life, one side has not. No, life occurs at the scale of planets. And as far as we know, we're the only one. And there are three theories. There are three plausible theories of how we could actually, life could have started here. It could have been created, it could have been sent here in a rocket ship, or it could have evolved in the primordial soup. All are plausible, but what we do know, what's incontrovertible, is once it got here, it evolved. And all life today has a common ancestor that goes way back, some 3.5 billion years. And so we have this evolution by natural selection that has led to this massively wonderful, spectacular world that we live in. And like Andre the Giant says, you must obey. Well, life must obey the laws of chemistry and physics. And in some respects, physics sets the stage, chemistry provides the materials and the assembly, and then we have biology, which is evolution through natural selection. We happen to live in a wonderful spot. We live in the Goldilocks zone. It's not too hot, not too cold, just perfect. And it's been that way for billions of years. The Earth gets its energy from the sun. And because the Earth is a sphere, the energy comes in, it's more concentrated at the equator, and it spreads out towards the poles. And the amount of energy coming in must equal the amount of energy going out at night. So, for instance, right now it's getting colder at night, and we're actually seeing the whole temperatures drop, and that's the reason, because our nights are longer than our days. But in many respects, we get about 1,300 watts coming in to the equator per meter square. That's about like a hairdryer that you probably used. You know, you look at your jumbo hairdryer, 1,500 watts, something like that. That's about what's coming in. And so this is a nice map that shows the mean temperature, and it shows that it's colder at the North Pole, and it's warmer at the equator. And that's the result of us living on a spherical Earth with the sun 90-some-odd million miles away. That also sets up what's called a circulation zones. We have the Hadley cell and the Ferrel cells and the polar cells. This is because as the sunlight comes in at the equator, it heats it most there, and we get this circulation pattern. And that results in the trade winds that we have, and it results in the upwellings and the downwellings. And most important, it results in what we call the intertropical convergence zone, this band of clouds that you can see. And this band of clouds is where the air is rising. And as the air rises, because it's heated, it condenses. It's like a pop-up thunderstorm on a summer afternoon. And that descends at about 30 degrees north and entrains another cell called the Ferrel cell, which in part then interacts with the polar cell. So the atmosphere is taller, it's higher at the equator, and it moves towards the poles. But where it is going up and we're getting condensation, we get rain. Where it comes down, it's dry, and we get drier weather. And this will give you an idea. If you look up there at the top, you'll see the Earth, you'll see the dry zones and the wet zones. And this happens to be a mapping by NASA showing where the water vapor is and where the rainfall is. So you can see that the tropics are much wetter than the more northern temperate regions. And that's resulted in life essentially living in different parts and evolving as different life forms. And we have the great biomes that go from the tundra in the North Pole all the way down into the tropical rainforests. So this different kind of life doesn't live there by accident. It lives there because it's evolved there over the last couple 100 million years. And all of it runs on solar energy coupled through photosynthesis. So we have photosynthesis coming in, fixing carbon dioxide, which is in red, turning it into sugar. And then respiration is when you eat something, you actually carry out respiration, you turn that sugar into usable energy that you can use. And those global cycles, that essentially that organic cycle of photosynthesis, respiration is what is powering life. That's where we get our energy. And these cycles are coupled to the Earth's energy balance and also the water balance. So essentially you have energy coming in as light, being used by the biosphere and leaving as heat. And that heat is, a lot of it's being reflected. We have photosynthesis and respiration, and that's what forms the energy to drive the food webs that we think of. It's sort of like a little choo-choo train. Remember the engine that could? It could because it can, and the biogeochemical cycles are what operates the planet. And really you could take everything bigger than a millimeter and get rid of it, and the Earth would still operate appropriately. But if you took everything that was larger than a millimeter and kept it and got rid of all the small stuff, the Earth would stop. It's the microbes that do the work for the planet. And over the 4.5 billion years or so of the Earth, I want to go over this because this is really the interesting thing. As life evolved, it began, the first organisms used carbon, used energy, and they generated methane. And they used a little bit of carbon, so you can see it pulled the carbon dioxide in the atmosphere down. And about 2.5 billion years ago, photosynthesis starts evolving oxygen. And the first thing that happened is the Earth rusted. We formed all the oxides. And after everything was rusted and none of the oxygen could be used chemically anymore, it began to leak into the atmosphere. And as it leaked into the atmosphere, we essentially changed the atmosphere, when we got to 1% oxygen, we ended up beginning an ozone layer. When the ozone layer began to develop, it blocked ultraviolet and allowed life to come up out of the deeper water into the shallower water. Eventually life came up on land. So what we've got happening is life has been sequestering carbon dioxide in the ground as fossil fuel. The reason it became fossilized was there was nothing there to eat it, because the plants came before the animals. That's simplistic. Now it is stored in a variety of places. We have the ancient coal forests that became coal. This is on land in the Silurian period about 300 million years ago. We had the stromatolites and the ancient reefs. All the old oil and gas fields that we work on now, that we go in and we get oil and gas out of, that all comes from ancient fossil reefs, because that's the reservoir for these. And then today we store, in terms of biomass, we store an awful lot of root material, carbon as roots in the ground. So you can see that we have oil and gas about 10,000 petagrams, that's 10 to the 15th grams. And we have about 40,000 sitting in the ocean, sort of storage there, and plants. So we have fossil carbon, and we have what we think of as green carbon. Then we have people. So we have this Earth that has drawn down the oxygen content, and as it's drawn down the CO2 and generated more oxygen, as the sun has gotten hotter, the Earth's temperature has roughly maintained the same for about the last billion years or so, plus or minus a couple degrees. And then we bring in people. And people have been increasing dramatically since 1750, this grant. And the little red bars, see the little red bars? That's my career at the College of Charleston, my 40 years at the College of Charleston, roughly from 1980 to the present. And since that time, we've gone from 4 billion to about 7 billion people. So this is a recent phenomenon. This isn't something that's happened in the past. And in the 1800s, people started writing about it. This is Popular Mechanics, March of 1912. And it was in the 1800s, the French Fourier and Pouillet started talking about the soot that was burning was making a blanket around the cities, and they were warmer. And finally, in the 1950s, Roger Revelle at Scripps Institute of Oceanography got Charles Keeling to come in and actually start measuring carbon dioxide in the atmosphere. And what we've seen is the atmospheric concentration of carbon dioxide has gone up, and the emissions from burning fossil fuels has gone up. And it comes from a mix of burning petroleum and coal and gas and cement, making cement, which is about 15% of it or so. So, and this is sort of the beginning of the Industrial Revolution. It's like a greenhouse. And what happens is, as the CO2 increases, it acts more like putting glass in the way. Glass will allow visible light to penetrate, but it stops infrared light from leaving, and that's why a greenhouse gets warm. And so carbon dioxide and other greenhouse gases actually absorb the infrared radiation that is trying to leave the Earth. It's being essentially re-radiated out at night. So what's happening, just a little bit of that's being trapped, much like a greenhouse, like this Biosphere 2 greenhouse. Now, around 1970, when computers became famous and we started using them, I guess you'd say, you know, the Apple I computer just sold for $400,000. You know that? That's amazing, isn't it? I should have kept all my old stuff. But anyway, the Club of Rome was formed. There's a bunch of people in Europe and at MIT, and they tried to model what the world was going to look like in the future. And they showed the population increasing to about the middle part of this century, then slowly decreasing as the age distribution changed. And that happens around that time. We have industrial output peaking and food production peaking, and pollution comes a little bit further. But what they were showing basically was that, hey, we're going to be using the resources of this planet, and the quality of life is going to go down. And you know what? This is really an accurate prediction. It's been pushed forwards by technology, but it's really stands pretty accurate. And you can go to the website Club of Rome and look it up, talk about it. Well, Mr. Keeling's data showed that the carbon dioxide in 1960 was increasing. And people used to say, oh, it goes up and it goes down and it increases and there's a cycle. Yes, there's an annual cycle. For example, in the wintertime, there's more carbon dioxide in the atmosphere in the northern hemisphere than there is in the summer, because we have more respiration and we have photosynthesis. But overall, we see that it's actually increasing, and we're now over I think we're over 415 parts per million. Okay? And the result of that is as that's been happening, we see that the Earth has been getting warmer, and we see a slight increase. 93% of the excess heat that's absorbed has gone into the oceans. The upper 2,000 meters of the ocean is warming. And it's been said if it wasn't for the oceans, the temperature on land now would be about 120 degrees Fahrenheit. If you look at it a little bit closer, you can see that, yeah, the Earth, we had a little more higher CO2, it had high CO2 around 120,000 years ago during the, and then slowly it decreased, and then it started to increase again, and then with the Industrial Revolution, it began to increase at rates that are thousands of times faster than it normally would. How hot is it going to get? Well, it's not just going to get uniformly hot. It's going to get hot all over. It's going to be hot in different places. Now, a lot of my friends, I have a friend who's a plumber, and he says, you know, I just can't get it. These little teeny people, how can we affect this Earth? And there's cycles, and there's just cycles, and it's a cycle up and a cycle down. Well, there are cycles, okay? And this is the cycles for the last 800,000 years. And that's driven by what's called Milankovitch cycling, and driven by the fact that the Earth is on an axial tilt, and it wobbles back and forth. And that's what's caused the ice ages. But notice all of a sudden we get to zero time here, which is 1950, and we see this staggering increase. It's out of bounds of the cycles. So that sort of ruins that argument. And people go, oh, the sun's hotter now. Well, actually, the sun is cooler now. So we have this data. We have a really group of really interesting people called NASA that go out and collect some really good data. And then they say, well, it's not our carbon, it's somebody else's carbon. It's not fossil carbon. We're not doing it. We know by looking at the stable isotopes of carbon, we know that the increase in carbon dioxide in the atmosphere is the result of burning fossil fuels. It's incontrovertible. So that sort of ruins that idea. This will give you an idea. This is an image of carbon dioxide on the planet. This will give you an idea of most of it's in the northern hemisphere. That's because that's where most of the people live, right? And most of the land is. But look at the patterns. It's not even. It's really sort of with all the circulation patterns of the world. And you can see concentrations of it, like over in Southeast Asia and China. You can see that dark area. and sort of to the west of, to the east of Europe, you can see it, and you can see it over North America. So it's really swirling and whirling. It's pretty heterogeneous. And this is because there are a lot of different gases that are what we think of as greenhouse gases. Carbon is the largest, and on the red side, that means it's capturing heat, and on the blue, it means that we're reflecting heat. So things like aerosols and white land and a white roof, that will reflect heat, but things like ozone and black carbon on snow will actually absorb heat. And when you add it all up, it's about 1.6 watts per meter square. Now, a new study just came out and said it's 0.7 watts per meter square. So if you take that and you put it over the amount of energy coming in, which is roughly 1,300 watts per meter square, it's like 0.05%. And this is why people can't get it. How could that, like if you were driving, suppose you were driving down the highway and you were driving 100 miles an hour was the speed limit, and you got a ticket for going 100.005 miles per hour. You'd say, come on, you can't be serious about that, right? Okay? People don't get it, but this is a constant, steady warming over all the time. It doesn't stop. So the other thing we're doing is, remember I said the forests pump down CO2. Well, we're chopping down the forests as fast as we can. So we only have about half of them left right now. So we're burning the candle at both ends, so to speak. How bad's it going to get? You all remember Bartholomew and the Oobleck, right? The king that didn't like the average weather and wanted something else. But what did King Diwar, what did he say when it was all over and he made it go away? He said, I'm sorry. Well, that's not going to work this time. This is about a 10-year-old image of different places that climate change is affecting the world. And notice there are no forest fires in here yet. This is 2008. So there are no forest fires yet and stuff like that. But you can begin to see that climate change is going to be striking all over in many different ways. It's not just one common sort of force that just causes floods and forest fires. This is the change in temperature that's predicted on the planet if we have 1 degree, 1.5, 2, or 4 degrees. Now, as Queen Quet suggested, when it gets hot enough, you can't breathe, right? It turns out at 95 degrees wet bulb thermometer, that means 100% saturation, 95 degrees, you cannot cool your body enough to stay alive. And so we have heat events that come in, these giant heat waves. In Paris, 15,000 people died in 2003 from a heat wave. In Oregon, just this past summer, over 500 people died from the heat dome that occurred. This is going to happen more and more and more. And the reason for this is that as that Hadley zone takes in more energy, it grows. And you notice that it has expanded to the north. And so the descending air that's the dry zone has gotten wider. This is why we're having droughts where we do. This is why there are areas that are now drying out. I met a scientist one time said, if you want to have animals in the Southwest, you better start raising goats instead of cows, because they can eat the brush. So what we have is the Hadley zone is pushing into the feral cell, and the feral cell is pushing into the polar cell, and it's making the whole thing unstable. The New York Times just published this little piece of paper that was about habitability in 2070, and what they said is that in 2070, I'm sorry, climate migration is going to result because there's going to be about 20% of the Earth that will be uninhabitable in another 50 years. And guess what? All those people at our border, in the southern border, coming from Guatemala, they're coming up here because their crops are failing. And our crops are going to fail even more when it gets hotter. We're going to see upwards of a 40% decrease in corn production and wheat production as it gets hotter. So that's going to drive more instability and more political instability. If you fly, like I tend to do a lot of intercontinental flying sometimes when COVID allows me. If you fly over the Arctic ice, you can see, this is a trip from San Francisco to Hong Kong, you can see the ice just pouring out of the northern areas. And the sea ice has been disappearing faster than our best models. So every time we create a model that says this is what's going to happen, like the Club of Rome, it's occurred faster. And the instability of the jet streams is causing havoc too. Hurricane Sandy made a left turn instead of a right turn and devastated the Northeast. And it's thought that because of the lack of sea ice, there was a blocking high that formed and allowed that storm to go in a different direction. We're getting rain bombs. This was one of the first rain bombs that talked about. What happens is the intertropical convergence with all that water, you get filaments that split off. And these filaments that split off and will carry 3 to 5 times as much water as the Mississippi River. And where they end up hitting land and hitting the mountain range, you'll get massive amounts of rain. This particular one in 2011, they had 17 inches of rain over a 1.5 day period. Gee, a couple of years ago, didn't we get like 30 inches of rain in South Carolina? Yeah, welcome to rain bombs. Malaria and other tropical diseases are going to move north because the vectors of those diseases can move north, along with pythons. And by the way, I have an armadillo trying to burrow a hole under my house right now. Same thing, they're moving north. The sea level that we're measuring and the sea level that we thought that we'd predicted is actually increasing over time. And the increase now, the rates, you can see the rates between 1900 and 1990 are lower. They're almost half of what it is between 1993 and 2010. And this is only going to accelerate. If you melt Greenland, you add 7 meters of 7 meters to sea level. If you melt the West Antarctic ice shelf, you add another 7 meters. 7 and 7 is 14 times 3. It's about 45 feet. And you can see it. We fly over Greenland on the way home one time in the summer, and you can see it. And Greenland is losing 235 gigatons per year of ice. 235 gigatons. That's a lot. Okay? And sea level all around the edges of the world, we're going to see increasing. And with 8 meters, we will essentially lose Florida, Charleston, the whole East Coast. Almost every city in the United States that borders the coast will be in trouble. Sea level's been a lot higher. In the Miocene, that's about somewhere between 5 and 20 million years ago, when sea level was quite a bit higher, coral reefs responded to that and they grew higher. And this is off the north coast of Jamaica. These reefs are about 100 feet high. So sea level gets higher, and it can continue to grow higher. It won't be this high in our lifetime, but if we keep doing what we're doing, we can accelerate it. Now, I study reefs, and I study reefs out of fascination of the biology of them and the evolution of them, and it's heartbreaking. This is a reef we call Symphony Reef because it's so beautiful, it's like playing a symphony. And this is Symphony Reef in 2016, bleaching. And corals with their hard skeletons, they actually eat zooplankton as well as use the algae to generate energy and help them grow. But soft corals, a lot of them don't feed on anything. They just grow on the algae. It's like having internal plants. And when they bleach, they start to starve and they start to metabolize themselves and they just disappear. And when you see reefs like Symphony Reef, this is 2014, and 3 years later it looks like this. And you watch the reefs in the Florida Keys go from this to this, okay? It's like a war zone. Can you imagine the world without reefs? That's where we're going. But imagine the world without so many different ecosystems. It's not just coral reefs. Coral reefs are the spectacular ones. But look what's happening to our forests. Look what's happening to our deserts. Look what's happening to all those ecosystems that generate the life support system that we call home. So I feel a little bit like right now we're sort of like the Who's in Whoville. And there's this big, giant, global melting Earth, this thing we call climate change, about to roll down on us. And we've only seen the very, very beginnings of it. You know, when Hurricane Dorian came in and sat over the Bahamas for 2 or 3 days at a Cat 5, that's just the beginning. That's just a little bit of sort of an hors d'oeuvre for this banquet we're being invited to. And here's the choice. It's very simple. If we stop using carbon fuels, stop using fossil fuels, and really work on as hard as we can hold the temperature. But if it's business as usual, forget it. Now notice this is max at 2 degrees Celsius. If we go past 1.5, we're in serious trouble. Serious trouble. We're already in trouble, but it gets worse. Okay? So I want to leave you with this. Every dollar you spend is a vote on how you want the world to be. We know how to do it. One of my mentors, a guy named Jacques Cousteau, wrote an essay called The Long Term Has No Price, in which he said, it doesn't matter what it costs to keep that marsh, as Queen Quit was saying. It doesn't matter. You want to build something, we need to have this economic benefit. No, the marsh is worth more. We need a biosphere that functions, or we don't function, period. We know how to do it, you know. All we have to do is figure it out. And the best logic of all is nature. So with that, thank you.